Hello everyone, my name is Odarike Charles, and today I'm going to show you how you can be able to do control simulation, specifically for time domain analysis using one MATLAB, using two Python. So you're going to have the problem, numerical problem, see how to solve just by hand, and also have a simulation in it and try to see what we can get out, how fast can we do a simulation project for control. So I have the document, so I can go to my document where I've saved the work. So I can go to files, file. I think I've saved it in doc. Okay. Yeah, I can go to desktop. Yeah, then Odari workspace. Then the project is Odari tutorials, control, time domain analysis. Then you have the document here. So this is the document. This is the numerical problem. And if you see from this numerical problem, just a second order transfer function for which is 25 over s squared plus 6s plus 25. So there are different types of second order for which we have the undamped where the damping ratio is equals to 0. We have the critically damped for whereby the damping ratio is equals to 1. We have the underdamped where the transfer functions lie between 0 and 1. And we have the overdamped for which it takes time to reach to the reference for which it's greater than the damping ratio is greater than 0. So how can you find the damping ratio? The second order has a characteristic equation that gets this characteristic equation is the one that can tell us about the stability of the system, and also it gives us the characteristic equation for which when you equate it to 0 it can give you poles. So from that, we always have a structure. When the s squared has a unit coefficient, I mean one coefficient, we can see the structure here. Let me try to, yeah, we can be able to see the structure. So the structure is always like, I didn't write it. Yeah, the structure is equals s squared plus 2 damping ratio omega ns plus omega squared. So when this is equals to 1, make sure that is equals to 1 so that you can be able to have it normalized or in the standard form. For that, you can see that 2 epsilon omega, and not epsilon but zeta, or that damping ratio, this value here, this coefficient 2 is equals to what? Is equals to 6. So the first thing you should know able to know is if the damping ratio lies between which range, then you can know the type of the system. So if you want to do that, you can equate two. You can start with finding first the omega square. So omega square is equals to 25. So you know the answer is equals to omega square 25. So when you do the square root, you get the natural frequency omega n is equals to 5. So from this now, you can be able to find the other coefficient, which is damping ratio. So equate to damping ratio omega n is equals to 6. We find that our damping ratio is equals to 0.6, for which tells us this one is a underdamped system. And you know the underdamped system, it is characterized by all the time domain analysis specification like peak time, rise time, decay time, and all that. So you can see that the damped frequency omega d, damped natural frequency omega d, it is just omega n to the square root of 1 minus damping ratio squared, of which is equals to what? Is equals to 4. So from that, you start to derivation of the time response. What you are interested is to find the rise time, of which is equals to 0.554. We have the peak time, of which is equals to 0.785. We have a maximum peak overshoot of 9.48, which means you take 9.48 plus 100 multiplied by it, because you have a unit step function, which means it'd be like the overshoot will be more. So we see that the settling time for 2, like 0, we allow only some desired or the error that we allow in the oscillations as it approaches what? Infinity. So that error is what we call the settling time. And time takes to get that value, that you are the desirable error into the system. So we get is 1.33. Then these are the values tabulated, and you can be able to see this the MATLAB now. The values from the MATLAB. This is just a sketch. So I'm going to generate all these. So the idea was, you see, by hand will take a long time. It will take a bit of time, not long, a bit of time to do these whole calculations, for which you can be able to use other systems that can be able to help you. So let's dive into MATLAB and be able to see how you can be able to do that. So let me go to the project, navigate to the project. So CD desktop, you can be able to see, okay, CD Odari tutorials, CD Odari tutorials, CD control, oh, sorry, yeah. So you can see that's the time domain analysis. So I have this work on my GitHub. I'll leave the link into the comment section so you can be able to see and you can interact with the code if there's any issue you can raise. So I'm going straight to MATLAB. So from this MATLAB, if you can see from this time domain analysis, I have a folder called simulation. So you can head to simulation. You can see that you have control simulation in MATLAB. Then I'll add another file for Python just right now. After doing the simulation using MATLAB, I'll show the other one. So you can be able to use Python to do the same. So you see the control live script file. So I can just click this file. Then now I'm going to write my code using this. It's taking quite some time before it configures everything. Yeah. So from that, you can be able to see that. Let me split the screen to see that. Our transfer function is equals to 25 over s squared plus 6s plus 25. So I can call it a system because mostly it's called system. So I can call it a system is equals to the transfer function. Let me start this. So the numerator is equals to just, you have only one coefficient of which is 25. So you can have 25. The denominator, the coefficient for s squared is equals to 1, for coefficient for s is equals to 6, then coefficient for just the constant time is equals to 25. So from that, you can be able to have a system of which you can say transfer function. We call the numerator, we call the denominator, then we can be able to see how it looks. So yeah, we are just done with that. So I can be able to adjust this. It's taking some time to configure everything before it runs. Yeah, so you can see the system is equal to 25 into s squared plus 6 plus 25. So from that, now we have to do because it was our input was a step signal, so input step signal. So for that, I don't have to do all the I find the inverse Laplace transform because when I'll show you everything here, but the easiest part is just to do this. So if you just type step, then you have the system. Okay. Just taking some quite time to do that, but we'll have to wait. Yeah. So let me have some grids. Let's say grid on. Yeah. So I can open in a different window so that I have such an interactive. So yeah. So this is the response of the system to an input signal, an input step signal, and you find that there's some peak value because you said that because we had a peak value of 9.8, so 9.8% we add 1, we get 109.8. So we multiply by 100, we get it was having some overshoot of around 1 point. That value, the highest value, the peak value is around 1.09. 1.09 something. We'll see from it if it's true or false. So the first thing, if this is the window, then you right click. When you right click, you'll have to see something like the response. You see something like characteristic, then yeah, let's start with the rise time. So it will hover for you, it will show you where the rise time is, so you can hover on this. It gives you a rise time of 0.371. We can hover to peak response, then we can see the peak response. We have an overshoot of 9.78, of which it is just the same of what we got just doing the calculation. So you see it was 9.8. So from that, you can be able to go to settling time. You can see the settling time is around 1.19. Let me hover to this. Then the time is equals to 0.78 for the peak, to reach the peak. Then yeah. So this is how you can be able to do the simulation, how you can be able to visualize it, and you see just a simple, very simple thing, right? So instead of me hovering and hovering, because the graph just to get me visualize the things, I can be able to get the information easily instead of me now hovering on the figure. So the easiest way I can do that is to do this. You can be able to say step info, then you have the system. So step info will give you the time domain specification. So you see, so these are the fields. Instead of me having to over on the figure, I can just have the step info, then have the rise time of 0.371, the transient time, the settling minimum, settling maximum. Then you have the overshoot, of which we say it was 9.78. We have the undershoot. Now undershoot, you have a peak of 1.0947. That's the the value of the peak. Because I told you to get the peak, you take 100, you add 9.78%, then you get 109.8%, then you multiply by 100, whereby you get 1.0948. So that will be the peak time. So this is how you can do the simulation using MATLAB. For this, you'll find the script in my GitHub, which is in the comment section. So from this, let me use now Python to do it, because we have done using this MATLAB. Some people are not good with MATLAB, some people are good with Python, so I'm going to show you that. So to do with Python, I'm going to use Notebook to do that. So from here, I can navigate back, I think, navigate back, then I can be able to navigate again. Yeah, so I think, okay. So let me use this one so I can see this other tutorial. So I'm going to run the Jupyter notebook here. And also, if you want to configure your terminal to look like mine, very simple. You can ask, and I can be able to answer. So from this, I can say Jupyter Lab. So if I Jupyter Lab now with the Python, I'm starting the notebook. So I can wait for a little while it configures everything. Yeah, our server started. Now everything's set up, and let's head to this. So you can see I'm going to use Python. I could be able to use MATLAB kernel. And also, if you want to know how you can now configure your notebook with your MATLAB, you can ask in the comment section. Let me head to Python. I wanted to cut this file. Let me get it to trash. I want to get it into this folder here, folder called simulation. Then I have a notebook there. Then I say, I'll rename it to control simulation. Let me call it Python. So I'm going to install the following library. Now I'm going to one, import numpy as NP for numerical operation. Import notepad class. Sorry, I can say from control import MATLAB as a MT from matplotlib dot import pyplot as plt. Instead of using those from, you can just say import matplotlib.pyplot as plt, import control.matlab as mt, instead of these all repetitions. So I can say import science plots, so that I can configure my plots to look like a scientific one. So I can be able to import again import seaborn as cns. Then I can configure my MATLAB plots to look scientific. So I can say science. Then, because I have an issue with my configuration for latex, I can say no latex. Then I can run that cell. I think I can remember the transfer function, so I'm going to just have the transfer function, because the numerator was 25. The numerator, so I can have the numerator was 25. Then the denominator was 1, 6, 25. Then you can say the system is equals to, we can use, because there's so much, I can say that import control CT, and I can be able to say, because there's some issues with the yeah, we have something that have been duplicated in MATLAB, so I'm just trying to hide, so I can say no. So from this, we have our system is equals to what? mt.tf transfer function. So you see, if you're like everything that you are done using MATLAB, you can now transfer, because you saw that to get the transfer function, what we did was just simple. We said that is equals to tf, because you are in the MATLAB now. But now when you come to Python, you have imported the MATLAB package. You just say mt.tf. Then you have to have the numerator the same way, the denominator the same way. Then you can see how the system looks like. So the system, this is the system we have, 25 into a squared plus 25. Then from that, I'm going to have the step. See, so you have to do the step. So, but now you have to do empty.step, right? Then you have the system. Run that cell. So you can hope it has brought out an array of values. So you see, this is the response. This is the time. If you don't know what it does, you can just have empty the step, then you can see what the values, the first array is for what and the second. So the first array for this response, see G, you can just say G. First one for the response, the second for the time. So you can see it's Y out time. So I can just have, let me call this the same way that I called, but it's not mandatory to call the same way. But like this, then I can have my system. So from this, I can be able to plot. So I can say plt.figure to have a figure. I can have a plt.figure, then I can have my fig size as 10 to 6. The width is 10, the height is 6. Face color, I can say white. Then I can now plot it. So I can say plt.plot. We have our y out, our t first, then our y out. So you can see this there. This is the response, of which we saw that it looks the same way we got from in Matlab. You see. So let me think have this as 8, this as 4. Just to, yeah, let me have it like this. So from that, let me add some information so that you can be able to visualize it well. So I can have label, I can say system response. Then I can have a latex of C of T. All this just to configure it well. Then I can have the color. Let me have it this color 00. This hexadecimal color, so B2. Then I can have a line width of 0. I think 2.5. Then I have to have that steady state value, so I can have it an horizontal line. Yeah, H line. I can say y is equals to 1.0. Color, let me have it as red. Then line style, let me have it as dotted. Line width equals to 1.5. Then have the label. I can say steady state value. I think that's like that. Then I can be able to close that. Then I think from that you can run to see plt.show. Yeah. So this is the response. Then this is the input. Then you can see how it takes you to get the input. So I think you can have that, and I can add this code here so that all this you find in the MATLAB. So of course I've already explained the MATLAB, so I have no time to do and to do all this. So you can see this is what we have, the step verification Python, of which I said in the comments. So this is what you can have. So what about now? We cannot be able to hover every time here. If I could have used Plotly, then I could have an interactive. Plotly gives you an interactive plotting, so you can be able to see how it does. So you can be able to hover around and see the values. But for this, so instead of doing that, I'm going to use all this. Don't worry about it. Just configuration to make a good plot. Yeah. But what I could have done, I can do away with all this. Yeah, I can do away with all this. Run. You get what you need, because what you want to see is how the response is, right? So all these you have to make it fancy. Let me say fancy, but to make it now in like visualize the information, because this I'm going to use this one into the readme of the project. So from that, I'm going to have the information the way we did. So you can say step empty.step. You can see step info. The same way it is in MATLAB, the same way you implement it in Python. So you can say the system. Then you can see the data, the rise time, the settling time. We have peak overshoot of 9.78. We have the peak. You have everything we got from MATLAB, the same. So Okay, so after getting these values, now you see that we have done the simulation using Python and using Matlab, and you've seen that they relate on how you get the values, right? So after this, now I'm going to add a bonus. I'm going to show you now how we push the code on GitHub. I think that's the interesting part. And the first part thing, you can be able to use the graphical interface to do that, or you can be able to use the CMD, the command line. So I'm going to show you how you can do that. So to do that, I can come to my terminal here. So this is the project. You have our project control or direct tutorials. For this, I'm going to use all consistently to do other videos because other videos have been making an own repo for that. Now I'm going to use this direct tutorial as a one standalone repo for all these things that I'm going to do. So from this now, I'm going to make a file. I'm going to name it readme. This is PowerShell. Oh, PowerShell, you use new item. You say new item. So in shortcut, you have new new item, new item. Or in short, you can just say ni, then I can say readme.md like that, and I have a new get ignore file. You can be able to use CMD, so I can do away that. I can interrupt the notebook, so I can say less did one line. Yeah, so that tutorials. Yeah, so you see, you say type null, then text.txt. So what remember file you need to text.txt. You see, you can see it there, but I don't want that, so I can do away with text.txt. Then I'm going to have because you have that everything there. You have the git.ignore file. You see, and it visualizes that. You can see here. Then inside the git.ignore file, I'm going to use vim, then git.ignore file. Yeah, so I'm going to add. I'm going to insert this thing called this. If you come to cd control, oh okay, but I can just okay. So this is how I can be able to say. So it is called ipynb checkpoints. So I can do away with that, but I'll add every ignore file here. So I can escape, then I can be able to save. So this is what we call vim. I'm going to read about it. So I can have that into my git ignore file. So I can do away. I'll do away with this file here. So from that, I can now go to VS Code. So I have to type VS Code, then enter. Then it's open to you in VS Code. So if you have started this file, I do delete this file, and also I'll do away with this file here. So you have the simulation for the control MATLAB. You have the control simulation for Python and MATLAB. You have the figures. You have the document there. If you go to document, you'll find the document that you are reading on. We use this one. So I'm going to initialize. So to initialize, what you do, you just type git init, or you can use this git, git. So you can have an extension of git and also use. So instead of doing git init here, if I do git init here, you see the changes here. Yeah. So I've initialized the project. Then after initialization, now I can be able to commit. So from this, git status, you can see our project has been initialized in VS Code. So instead of doing the changes using the command line, let me use this VS Code to do that. So I can add this. So instead of git add, staging the file, just hit the plus sign here. Then I can say add git ignore file, right? Yeah, so I can say add readme.md file, then commit. So if you don't want to write those commits, you can just state the file. Then you can come and if you have the kilo code, you can be able to just see that kilo code there. Then it will generate you the commits. So instead of you doing all the analysis, reviewing the changes in the file, what you call kilo code can be able to generate for you the yeah, you see, just say doc time domain analysis add tutorial document.pdf. So you see, it commits for you automatically. So that's what I always use most of the time. So then I can add this figure. So instead of, so I can say add response MATLAB figure. And there are good ways of writing commits. So go and check out good ways of writing commits. So control simulation using Python, then add add control time domain simulation using is it Matlab. So I can be able to commit. So after committing, now is to do the remote and what do now to create a repo. But here you just have to publish the branch. So I can be able to publish the branch so that I can have the name of the repo. Then it will prompt for you if you want it to be private or public. So I'll have it public because I want you to access from that. So it will start to push. So publish to uploading files and everything. So you see it running there. And from that, I think we are done because afterwards, just if you go to check on my GitHub, um, GitHub, I'll find that. Yeah, it's open is in Matlab in GitHub. So I find that project or that tutorials very easy. So this is how you can be able to push a project to GitHub very easily without the headache of knowing, cramming, all those. Because everything that you can do with the command line, you can be able to do it here. If you want to push, clone, check out to maybe a certain branch, fetch, compose commit, generate commit changes, pull, push, branch, remote, state, anything that you do with the command line, you can be able to use it on the graphical interface. And this makes for people that they are not uh, well versed with command line. So you can see, you can exit that also. So you can see the project. Yeah, you have the control, the git file, the readme, and everything here set up here. So I'm going to add more information and the about. I'm going to add a good readme for this project, and I hope you'll follow my. I hope please follow my YouTube channel. Thank you.